You know how sometimes things just get stuck? Could be a chemical reaction that just stalls out or a particle that seems completely trapped. Well, it turns out physics is full of these moments, and a brand new paper suggests the reason isn't at all what we thought. It hints that reality itself might have a fundamental geometric glitch. So let's dive in and see what that actually means.
Right off the bat, the paper hits us with this pretty wild idea. It asks us to just stop and think for a second. This whole phenomenon of getting stuck, what physicists call metastability or tunneling, what if it's not some random obstacle? What if it's not a bug at all, but a deep, essential, and even predictable feature of how our universe is put together?
See, for a long time, the standard explanation was all about dynamics. To get from one state to another, you had to climb this massive energy hill. It's a slog. But this new idea, it says, hold on, you're looking at the wrong map. It's not about energy hills, it's about a hidden glitch, something written into the very geometry of possibility itself.
Okay, so to really get this, we've got to dig into what it means to be stuck in this deeper way. We're moving past those simple ideas of energy barriers.
The classic picture is super intuitive, right? Just imagine a ball sitting in a valley. If it wants to get to the next valley over, it's got to roll up and over a big hill. That hill is the energy barrier. And this has been our go-to explanation for, well, everything. From why some reactions are slow to how quantum tunneling works, it's always about having enough juice to make that climb.
But here is the big pivot. This is where the authors ask a really fascinating question. What if we've been looking in the wrong place this whole time? What if the reason things get stuck has absolutely nothing to do with hills and valleys in the three-dimensional space we live in?
And that question takes us somewhere totally new. We're about to go on a journey, but not through physical space. We're going to explore this abstract, sprawling landscape of every single possible state a system can be in.
This new world is called probability space. Now, it's super important to get this. You can't book a flight there. It's a conceptual map, a giant catalog of possibilities. Every single point on this map is one unique arrangement of a system. And a journey on this map, that's just the system changing from one of those configurations to another.
So with this map of possibilities, physicists can actually chart a course. They can track the evolution of a system, what they call transport, as it moves along a path from its starting state to its ending state. It's literally like drawing a line from before to after on this map of what if. Okay, but this is where it gets really strange. Because when scientists started charting these paths, they found something broken. There's a fundamental glitch in the most basic rules of travel. Something that should be simple just isn't.
Think about it like this. This is super simple. You walk from your house, point A, to the store, point B. Then you walk from the store, B, to the park, C. That total trip is exactly the same as if you just walked straight from your house to the park, right? A to B plus B to C has to equal A to C. That's like rule number one of moving around. Except, on this map of possibilities, it doesn't work. The researchers discovered that the path from A to B, followed by the path from B to C, does not add up to the direct path from A to C. It's like the universe's GPS has a serious bug, and the two routes lead to completely different results.
Now here's the math behind it. Don't worry, it's not as scary as it looks. In math, when things add up nicely, it's called functorial. But this paper finds that this transport is only weakly functorial. You see that not equal to sign? That little symbol is the entire mystery. It's the formal scientific way of saying the journey has a glitch. The paths don't add up.
So, if the basic rules of travel are broken, how in the world do you even begin to measure that? Well, as it turns out, mathematicians had already built the perfect tool for exactly this job. A way to map out the geometry of these glitches.
It's called a bundle gerbe. And I know, it's a wild name, but forget the name for a second. What matters is what it does. Think of it as a super sophisticated glitch detector. Its entire reason for existing is to find and precisely measure this exact kind of failure, where paths that ought to be the same just aren't.
And this glitch detector gives a reading. It's called its curvature. Now, this isn't about bent space-time or anything like that. It's just a number that tells you how badly the paths fail to line up. In essence, it creates a whole new map, one that pinpoints the hotspots in the landscape of possibilities where these navigational glitches are the most severe.
And this is the moment it all clicks into place. This is where that abstract, weird geometric glitch gets tied directly back to the very real, physical phenomenon of things getting stuck.
The paper makes this incredibly direct and powerful connection.
In physics, there's this thing called the spectral gap. It's basically a measure of how easy it is for a system to change. When the gap is big, change is easy. When that gap collapses down to zero, the system gets stuck. And the paper finds that the geometric glitch, the Gerb's curvature, is massively concentrated in the exact same spots where this spectral gap collapses.
And this makes the whole thing crystal clear. The spectral gap collapsing, that's the physical evidence of a system being stuck. And this new work shows that the geometric glitch is the physical stuckness. They're not just related, they are two sides of the very same coin. The abstract breakdown in math corresponds perfectly to a concrete barrier in physics.
And of course, they tested it. In simple symmetric systems where things don't really get stuck, they found basically zero correlation. But in the messy, asymmetric systems, the kind that have bottlenecks where things do get stuck, the correlation was over 95%. I mean, come on, that's not a coincidence. That is a smoking gun. The theory works.
So what are the implications here? They're huge. This is not just a new way to calculate something we already knew. This suggests that we might need to fundamentally rethink the very nature of the physical world.
This whole perspective just flips our old understanding on its head. A metastable state, that place where a system is temporarily stuck, well, in this view, it's just a safe zone on the map of possibilities, a region where you can wander around freely without hitting any of those geometric glitches. And tunneling? That's what happens when your only option is to plow right through one of those glitchy hotspots. The stuckness is just the toll you have to pay.
So here's the bottom line. Getting stuck isn't an accident. It's not a problem of energy. It's a geometric necessity. It's the price a system has to pay for trying to stitch together a bunch of local descriptions that just don't quite fit perfectly on a global scale. This glitch is a feature, not a bug. And understanding it could open up entirely new ways to control everything from chemical reactions to quantum computers.
The paper ends on this beautiful, almost poetic note. It suggests that some of the most important, most interesting things in our universe, the very phenomena that give it structure and create time itself, they exist precisely because of this elegant geometric imperfection. A glitch, it turns out, might just be what makes reality tick.